Good afternoon, Precal students. I hope you're doing well. This video is over section 11.5, polar coordinates. Polar coordinates are very cool. We're going to be using them to graph a lot of conics because something that's very complex in rectangular coordinates, which are x and y, what we're normally used to seeing with the Cartesian coordinate or the UV coordinate system. Something that's very complicated using that system can be expressed very easily using the polar coordinate system. So that's the reason why we're doing this, okay? So in the polar coordinate system, we're going to start with a point that's going to be called the origin, where they're going to have a horizontal line extending out from the origin. Instead of x and y, our variables are going to be r and theta. You guys may have seen these before from our discussion on polar form of vectors. This is going to go back to it. This is what it ties into. So, in the polar coordinates, r is going to be the distance of your point from the origin. Theta is going to be an angle that's formed from the initial ray of the horizontal line to the terminal ray that lies on the point. You can see that clearly in your book in this picture right here, where theta goes from the polar axis to our new line, and our point is right here at r theta. So, a couple of things to keep in mind when we're talking about this then. First and foremost, our angles are going to be in radians. So we're going to start with 0 on the horizontal line, pi over 2, pi, 3 pi over 2, and 2 pi. Because we're dealing with radians, we're going to have several points that do not have unique coordinates. For example, anything that has a coterminal angle is going to share the same point. Pi over 3 and 7 pi over 3 are two examples of coterminal angles. Coterminal angles are just going to be multiples of 2 pi because you go around the polar coordinate. Okay? In addition, negative r's on polar coordinates are going to be the opposite side of where they should be. So, if we're looking right here at negative 4 pi over 2, you notice pi over 2 is this theta right here. 4 is the distance out here. Negative 4 would be opposite the pi over 2 angle. That's another way in which we can have non-unique coordinates. Alright? So, that's your introduction to polar coordinates. They're very cool, very useful. We're going to need to be able to convert between polar and rectangular and polar coordinates. You guys have already done this before using your vectors. That's why this may look very familiar to you. Our x term is going to be r the cosine of theta. Our y term is r the sine of theta. And then our r will be equal to the square root of x squared plus y squared, and our theta will be equal to the tangent inverse of y over x. You just plug stuff in to switch between the two types of coordinates. Like I said earlier, we can use polar coordinates to make a complex rectangular equation very simple. If you remember, a circle or an ellipse is x squared over a squared plus y squared over b squared is equal to 1. Well, a circle in the polar coordinate system is just r is equal to 3 would be a circle with a radius of 3. Very easy to write, very easy to graph and understand. Certainly much more easier than that second degree fractional equation. Okay? We look over here when we're just given our theta, it's going to be a line. So if we're just given r, it's going to be a circle. If we're just given theta, it's going to be a line. If our graph has both r and theta, it's going to be a conic, which will have curves. Okay? So this one is a little bit more complicated, this graph. R is equal to 1 plus the sine of theta. Whenever we're graphing something in the polar coordinate system, we're going to have to look at how the value of theta changes as we go around the circle. So when theta is equal to 0, the sine of theta is 0. When theta equals pi over 2, the sine of theta equals 1. When theta equals pi, the sine of theta equals 0. When theta equals 3 pi over 2, the sine of theta equals negative 1. When theta equals 2 pi, the sine of theta equals 0. So you'll notice that we'll have a whole bunch of different values of theta as we go in a revolution around our origin, and that's going to change our result right here, what we're graphing, okay? So whenever we graph this r equals 1 plus the sine of theta, it's going to look like this. This is a special, unique shape. There's several different types of unique polar shapes that are found in your book on page 742 and 743. They're right here. They include a Archimedean spiral, a carotenoid, which looks like a heart, a rose, a circle, a lemniscate, which looks like your infinity or 8 symbol, and a limicon. All right? All of these shapes are formed from polar coordinates. You can see the equations for them there. Okay, so the homework should be fairly simple for tonight. The first couple questions, they just want you to give you a possible polar coordinate. And then in 2 through 6, they're looking for other pairs from 3 pi over 3. In number 1 right here, I did point P for you. If you look at this, each concentric circle going outwards is going to increase your value of r. Our value of r is between 1 and 3, so it's 2. Notice we're on the line pi over 4, so this point for P, a possible coordinate, could be 2 pi over 4. I did number 2 in this section for you. We're given 3 pi over 3. So we're trying to find 4 other pairs of polar coordinates for this given point. We can either use a coterminal angle by adding or subtracting 2 pi. That gives us our first values here where our r stays the same. Here we add 2 pi, here we subtract 2 pi. In the second one, we can change our r to negative. When we do that, we're going to be using the opposite angle. So that's where we get the 4 pi over 3 and 2 pi over 3. Okay? Because these are the opposite angle to pi over 3. In number 8, we're going from polar rectangular form. Remember, x is equal to r the cosine of theta. So we just plug in -2 and our theta of pi over 4, and we do the same for sine. And then we simplify, and we'll get negative square root of 2, negative square root of 2. Rectangular polar, still very simple. Our r is equal to x squared plus y squared. We just plug x and y in. Theta is equal to tangent inverse of y over x. We just plug our y and x in. Be very careful with your parentheses and make sure you're in radian mode. And you should get negative pi over 6. If you aren't sure whether you got the correct answer in terms of pi, just experiment with dividing pi by a numeral that you think it might be. Okay, so the other type of problem you'll be doing for this section is making graphs. I did number 36 here for you. We're doing the equation r is equal to 1 plus 2 the cosine of theta. It's very useful to go ahead and just make a table to help you keep track of how your second variable, the theta, is going to be changing, how it's going to be changing in response to different values of theta as you go around the circle. How your r is going to be changing in response to the different values of theta. So we go theta 0, pi over 2, pi, 3 pi over 2, and 2 pi. Well, the cosine of 0 is 1. We multiply it by 2, we add 1. The cosine of pi over 2 is 0, multiply it by 2, add 1. The cosine of pi is negative 1, multiply it by 2 is negative 2, add 1 is negative 1. The cosine of 3 pi over 2, 0, 0, 1. And 2 pi, 1, 2, 3. So then at our graph, we need to make sure that at all of these points going around, which you can see, the theta is acting like our little signs on the clock as we go around the circle. We need to make sure that we start at the origin, and then at each spot, each angle, we need to be at the correct r value. And when you do this correctly, it's going to end up looking like this. If you would like help with this part, I'm more than happy to help you, and I can show you some cool calculator tricks for when you have to do something more accurate than sketching. Now, this has been a rather long video, but it's pretty simple material. And as always, I'm looking forward to seeing how you guys do and helping you where you need it. I hope you guys have a great day.